So let's go ahead and shift gears. We'll get into section 7.2, which is shear and moment diagrams. All right, so the objectives of today. We are going to learn today to solve for the shear, which is V, and moment, which is M, diagrams using graphical calculus techniques. Now, graphical calculus techniques basically means that we're going to focus on, and I guess I'll just put that here, that's number 2. So this idea of graphical calculus techniques just filters right into here. Relate values, so function values or values, slopes, and areas. Right? Fundamentally, if you have an equation and you take the derivative of that equation, what do you have? The slope, right? You have a function of the slope as it varies with length. And if you have an equation, you take an integral of equation, you have an area under that curve, right? So we're going to use basically just those two relationships. As I talk about this graphical calculus techniques, we're going to focus on areas and slopes. All right. So the basic theory here is that if we have a beam, and let's say this beam has some support forces and has some sort of a distributed load on that beam, then we can take a slice of the beam and a slice of the distributed load. I could draw that over here, draw a free body diagram of this little slice. And we can say that this slice has some length of delta x, right? So this is my little delta x slice. It has a distributed load. It's going to differ along its length. So I could say that this is defined by, this is W as a function of x, the loading as a function of distance. And in all these problems, we're going to use an x-axis that just goes horizontal to the beam. I'll also say that for all shear moment diagrams, we'll be using horizontal beams, and that's it. Okay, just as we build this tool, we just focus on horizontal beams. And if I took two cuts, right, this is like one cut here and another cut there, I've exposed the forces that are inside that beam. I can assume positive shear going up because it's opposite the right-hand rule. Wrapping around the other side, positive shear assumed going down. Both my couple moments, M, internal, will be going up to make that beam smile. Now, if I have a changing load from the left-hand end of that little slice to the right-hand end of the slice, I need to add in a change in that moment, right? The moment on one end is not exactly equal to the moment on the other end because the load is changing across the top. It's also true here of my shear, so V plus delta V. I have a change in the shear from the left end to the right end. So really what we could look at this and say, well, this is a free body diagram, and I could solve this free body diagram. And when you work through the solving of that free body diagram, and really what we do in that is we look to solve for what is delta M and what is delta V, and we find out that our delta V is equal to the integral of W sub x dx. So to put that in words, we can say the change in shear is equal to the area under the loading curve. Right? Loading curve or loading function. Change in the shear is the area under the loading curve. And then over here on the right, we have delta M, change in our moment, is our integral of V sub x dx. And so this very similarly is the change moment is equal to the area under our shear. So if we know that the change in the shear is the integral of the loading, we can think that, if I draw that we have, so we have our W, our V, and our M, but our three fundamental functions. So we have our loading, our shear, and our moment. We just said with these two equations that as we go down in this direction right here, that we're integrating. Right? We integrate load to come up with our shear. We integrate shear to come up with the change in our moment. And then if we go back up, right, if you integrate going down one direction, of course, if you go back up the other direction, you could take derivatives. And so if I take these same relationships, basically this same relationship between V and W, these ones here, this is a, you could think here we're focusing on integrals. And instead, if we focus on derivatives, we end up with equations that tell us that the value W is equal to dV dx, right? So this says that the value of, actually I'll just write this in the same form. Let me move this just a touch, just to put the definition below the function. I don't know why it's automatically moving there. It's going to run away. So this is the value of load is equal to the slope of shear. And then similarly, V is equal to dm dx. And this tells me that the value of the shear is equal to the slope of the moment. Moment shear load, yeah. Okay, so that's really more looking at the slopes versus the areas, the derivatives versus the integrals. Okay, so it's really kind of those four fundamental relationships. And you can think that you can have these same kind of relationships, right, between like position, velocity, and acceleration that you work through in physics. Those are the ones that we'll use in dynamics all the time. And they're just related by, we take derivatives to go from position to velocity, another derivative to go from velocity to acceleration. If you're given acceleration, you can go into integral, go from acceleration to velocity, another integral go from velocity up to position, right? Same kind of an integral relationship between these. And so if you want to use that in your brain as kind of a parallel structure, that works totally fine if you understand that fairly well. But these are really the four fundamental rules that we'll use, because I'm going to teach this topic in a way that's really going to lean on these relationships. And then we can solve most of these problems kind of graphically. You can solve them really fast. You can look at them just like the areas under curves and slopes and things and draw your shear moment diagrams. Sometimes without ever writing an equation. You can actually solve for not only the shape of the free body of the shear moment diagram, but also all of the values in the entire thing just by using these relationships right here. There's an alternative in section 7.2 where it's very equation heavy, and even for the easiest problem, you write all these different equations for your shear and moment curves. It works equally well. It's just that even on easy problems, it's quite a bit of math. On harder problems, it's even more math. And I kind of teach a way that if we can use this graphical technique to solve for the kind of easy to mid parts of a problem, if it's hard, we can substitute a couple of equations in there to get us where we need to go, and then we've got all the pieces together. So it's kind of the fastest technique. I also find it has the most intuition built into it. So you can look at your functions and really get a feel for, is this right or is this wrong? Cool.
So we'll be given one of these equations, and then we just calculate the other two.
Yeah, fundamentally what we end up doing, and actually let me just go through this example. So the question was, would we be giving one of these and would we be doing the calculus? You often start at the loading. What is the loading? And then you work down through from loading to shear to moment. So let's kind of look at a standard, the standard flow of a problem. So this isn't going to be a full numerical example. This is really just going to be more kind of a process example. So step one is that we're given a loading. And I'll put here also to find all support forces. I'll put forces / moments. You can't have fixed supports on this topic. But we don't have any room for unknown supports. We need to know what all of those are because like I said, we're functionally going to find an entire distribution of all of the shear, an entire distribution of all the moment. And so I'm going to have 3 columns total here. My middle column is going to be the graphical representation. And so if I have a uniform distributed load, let's say that's going down. In structural terms, they have both what's called live loads and also what's called dead loads. Dead loads aren't like zombies buried in the concrete or anything. They're just the fact that dead loads don't change. Dead loads are the weight of things that are bolted down like these desks, the weight of the flooring, the weight of the structural system, the weight of the HVAC system, the weight of the roof. Live loads are all of us, right, walking in and out. Other live loads are like wind and snow and things that can change over time. We call live loads. But you could think this is maybe just a dead load, a distributed load on that deck. And if we want to solve for these support forces, if we just assume it's simply supported, we can end up with a concentrated force here at one end and a concentrated force at the other. These would both be, I'll call them F1 and F2. We know that F1 is equal to F2, right? If it's a uniform load and these things are on either end, that those would have to be equal. And then the third column I'm going to put over here is going to be my equations. Now I'm going to backfill those equations. I'm going to focus on kind of the graphical technique, and then we'll backfill the equations moving down. So back to Cole's question, this is usually how problems are given. It will say, here's a load. Find the maximum shear, maximum load, or maximum shear and maximum moment on that beam given this load. Okay? And so step 2 is we want to integrate our W as a function of X, our loading, right? This is our loading to find V as a function of X. Okay, so often we'll draw these shear and moment diagrams right below their free body diagram, just so that we kind of spatially have things nice and lined up. This is a very simple load on this one. We label our shear diagrams V. All of the units in both the force diagram and also the shear diagram are just going to be force units, right? So let's just say that this is in newtons, then this is going to be in newtons. Okay, so shear and loading are both in just force units. And so if the change in our shear is the area underneath our loading curve, right? That makes really good sense for like this rectangular distributed loading. But what about those concentrated loads, right? What's the area of a concentrated load? It happens over no distance, right? It happens over 0 distance at all. So fundamentally, it's just a concentrated push on the shear. Okay, and so you're going to hear me use this word push a lot because we talk about that the loading pushes the shear, and it pushes it in the same direction that the loading was going. And so this would be a change in my shear of F1 because of that concentrated load pushing up a magnitude of F1. And then if we take a look at the effect of that distributed load on the shear, we have this other equation that tells us that the slope of the shear is the value of the load. Okay, and so, well, the slope of the shear, is it going to be constant or changing? Constant is going to be positive or negative? It's going to be constant, it's going to be negative because the arrows are pushing down, which means I have a load that's coming down. Okay, and so just put that little note on here that this tells me this is a constant value pointed down. Therefore, I'll put it here as V slope will be constant and negative. All right, so that's going to be constant. I'm just trying to scroll my screen. There we go. If that's going to be constant and negative, it will look something like this. And then here at the far end, if this concentrated load will push it back up, and I shouldn't have drawn that arrowhead there, technically. These are just graphs, not actual vector quantities. And so this would be the value of F2. We tend to shade these just so we can kind of tell what's underneath the curve. And the slope here will be rise over run. So this is going to be my constant value of W times a run of 1. Okay, so you could think that if this had a value of negative 2 newtons per meter, this is going to be it's going to drop negative 2 over 1 meter. Negative 2 newtons over 1 meter, right? So the value of your load is the slope of the shear. And then number 3, to take this a step further, is we're going to find the moment. And these axes here through the middle are all fundamentally like our x-axes, just a horizontal axis system. And so we now want to integrate v as a function of x to find w as a function of x. All right, so if the only vertical shifts in our shear diagram come from concentrated forces, cool, we'll get to that. Sorry, I wrote that wrong. Yes, we're not going back to the load. We're moving on to the moment. Integrate v sub x to find m sub x. And so if the only concentrated, or the only vertical shifts in the shear came from a concentrated force, where do you think the only vertical shifts in the moment diagram might come from? Vertical shifts in the moment diagram. Are there any concentrated moments? What is a concentrated moment? How about a couple? Are couples concentrated moment? Right? Moments that happen at one specific point. Okay, and so we're not going to see any vertical shifts. I'll just put it here. No vertical shifts in m as a function of x, my moment function, unless couples are present. Okay. And so if there's not going to be any couples, and the other thing about these shear moment diagrams, and this is a great tool to use, is that they always need to close to 0. Okay, you can't have a shear moment diagram that just kind of opens up the space and like never lands. And so even our shear diagram here, if you take a look at, what is the shear just to the left of that concentrated force, or what is the shear just to the right of that final concentrated force, those both have to be 0. Okay, so it had to close. It opened at 0, it jumped up F1, it came down at a constant slope, jumped back up at F2, and then closed back at 0. So same thing for our moment diagram. And if we don't have a concentrated couple on either end, it's going to start and finish at 0, right? Because there's no vertical shifts. And so we're going to start here at 0, and we're going to end here at 0. So if the value of our shear is the slope of the moment, will my moment curve start in a positive direction or a negative direction? Value of the shear is the slope of the moment. Positive, right? So, and if the value of the shear is the slope of the moment, what happens right in the middle of my moment diagram? I have a slope of 0, so it means it's a maxima or a minima. Because we're starting positive, we're hitting 0 in the middle, and then we're going down on the far side, it will be a maxima for this curve. And so this goes up like here. We hit a maxima right here where the shear is equal to 0, and then we drop back down to 0. So that is our moment curve. All right, now I'm going to fill in these equations. I end up writing a note here right in the middle of where I wanted to do some of that. Move that up there, okay. So I could write that for my equations, let me just delete this. It's valid, going too far there. I just want the space. Okay, so this is going to be my equations over here. And so we could say over here that w as a function of x is equal to, I'm going to write this in general terms instead of putting it here in terms of -2 newtons per meter. I'm just going to call this w, like a constant value of that distributed load. So w as a function of x is equal to negative w. This negative just to emphasize that it's going down. Right? If it was forces were going up for that distributed load. Now this function right here doesn't take into account the concentrated loads on either end. Right? There's no easy way just to to write those. Right? That they're but we do need to deal with them as we get down into our shear. So as we look at the shear, and we say that the shear, V, is equal to the integral of w as a function of x dx. And so we integrate, we get V is equal to negative wx plus c1. Right? And so if I integrate negative w, I just have to multiply times x, so I get a negative wx plus c1. What is c1 equal to? The constant, that's good. But what's c1 equal to in this problem as far as a variable? I didn't put a number to it, but it's a variable. F1, right? Where does the shear curve start? Right? That's what the constant value is. It's telling you what's the initial value of that shear curve. And so this value right here is F1. And then we could do this again, and we could say that our m, our moment, is equal to the integral. Sorry, I have 2 equal signs there. Moment is equal to the integral of v sub x dx. And so my moment is going to equal negative w times x squared over 2 plus, I'm going to run out of room here, plus f1 times x plus c2. Right? So I just integrated this function here. That's with x squared over 2. It's another integral dx. What is my value of c2 for that moment function? I had a vote of F2. Any other votes? What's the value at the start of the moment curve? 0. Right? That's all those constants are. It's the value at the start of the function. It shifts it vertically if you didn't start at 0. And so this one here is 0 because we started here at 0 for that moment curve. And so you can solve these either way. The thing that I like about this center method here is we didn't write a single equation, and we very quickly can draw these functions. The other thing that we know about this is that if we said that the integral under our shear is the change in our moment, so if I say, if this here I call integral of v, and it's over just that one section right there, didn't we say that the integral of v is equal to delta m? Right? So if I look down here and I say, well, this change in my moment from bottom to top there is simply equal to this integral of v or my delta m. Okay? So not only can I draw the functions, but I can actually find the value of that maximum moment simply by finding the area of a triangle. Right? And triangles are easy, 1/2 base times height. And so all you need to know is the F1 times half of the length of the beam divided by 2. And you'd have the value of the maximum moment. Okay? Or you could work through these equations here. the way that you do this to find the maximum moment, if you realize that it was at a maxima, is that you would actually set this shear value here equal to 0, right, and solve for where is the location of that maximum, and then you substitute that x value into your moment equation, you plug that in, and you say, all right, what's my moment at that location of x? Okay, so that's the equation-based technique. Now, the book actually teaches a third way. I focus on these two. I primarily use the graphical technique until the graphical technique gets too complicated, and that really comes down into if you're trying to find the area of parabolic curves, just our standard geometric relationships get to be quite a bit more challenging. So then if I end up needing those, I drift over to this other equation technique. Your book actually uses a technique similar to 7.1, where you take slices of this and solve for you use like an unknown location of, like, you'll say that this is some value of x over to some unknown cut point, and you write those shear, moment, and axial load equations just like you did in 7.1, but instead of being absolute, they're due to this unknown distance x. It works equally well. It just that I just find that the intuition is not as solid in that, but mathematically it works just fine. So it's kind of three ways, this being one way here, this being a second way, and a third way being out of section 7.2. I'll never even show you examples of 7.2. You're welcome to use it on exams. It's just slow, and that's my biggest beef with it, is it's just not a very efficient way to solve these. These two, 1 and 2, these both come out of section 7.3 of your book. So it's not that they're not in the book, they're just covered in a different section.